This lesson is an introduction to vectors in 3 dimensions. We know vector is a mathematical quantity having both magnitude and direction. So a vector in 3 dimensions is a line segment in 3-dimensional space running from point A, which is the tail, to point B, which is the head. Then we move the vector until its initial point, which is the tail, at the origin. Its endpoint, which is the head, will fall on some kind of point P with a coordinate A, B, C. So let's take a look at the diagram on the right. So this is a 3-dimensional space, and there's a vector AB, and we call them vector U. So once we move the point A to the origin, vector U becomes at this position, which we call them vector OP. And vector OP is the position vector of vector AB, which can be found by using this algebraic calculation. We say OB minus OA, which is the point B minus the point A, it will be the position vector AB, which is OP. Example 1. Now we're going to learn how to draw a vector in 3-dimensional space. So given there's a point P, -5, -7, and 2, how do I draw them? So we used to have x-axis here and y-axis here. So now we're going to say this is going to be the y, this is going to be the z, and the one that is at 45 degrees sticking out, that will be the x-axis. And usually we use solid line for the positive axis, and we use the dotted line for the negative axis. Now, let's put the points on. The x value is -5. So this is the x-axis because x value is negative, so we're going to go backwards on the dotted line. So we do -1, -2, -3, -4, -5. This point is -5. The coordinate is -5, 0, and 0. And the y value here is -7. So we know this is y-axis. So negative y value will be going on the left. So we will go -1, -2, -3, -4, -5, -6, -7. And the coordinate here will be 0, -7, and 0. Next step, we're going to create the base of the rectangular box, which will look like a parallelogram on our diagram. So at this x value, which is a -5, we have to pretend there is a y-axis here, and we're going to put the y value of -7 on. So we do -1, -2, -3, -4, -5, -6, -7. And at the same point, on the y value here, which is -7, we are going to pretend there is an x-axis, and we're going to go for -5. So we do -1, -2, -3, -4, -5. And you will see at this point, it's called -5, -7, and 0. And here we have our base for the rectangular box, which will look like a parallelogram. Next step, we know the z value is 2. That means on the base of the rectangular box, from every single point here, we're going to raise the point up by 2 units. So we're going to have 1 point here, 1 point here, 1 point here, and 1 point here. And we're going to make another parallelogram. And at this point, you can clearly see there is a 3-dimensional box. So let's label all the points that we have. This is the origin, 0, 0, 0. We raise it up by 2 units, will become 0, 0, 2. This point here, origin code -5, 0, 0. But we're going to raise it up by 2 units, so it become -5, 0, and 2. This point here, origin code 0, -7, 0. When you raise up by 2 units, will be 0, -7, and 2. And finally, this point here, origin is -5, -7, and 0. So this point will become -5, -7, and 2. After we have the 3D box on the diagram, then we can construct our vector OP. That means Our tail is at the origin, the head is at point P, and this is our vector OP in three-dimensional space. Before we can find the magnitude of the vector OP, I have to break into two right triangles. So the first right triangle is actually on the base of the rectangular box, which is right here. As you can see from this green triangle, there is a 90 degrees angle here. So we can find this side, that's called W. So we know W squared using Pythagorean theorem, we can write as negative 5 squared plus negative 7 squared, which is the x component and the y component of the vector OP. And now let's look at another triangle here. So there is another right triangle here, and that's labeled then with a blue triangle. As you can see from this blue triangle, there's also a 90 degrees angle right there. So that's labeled then with a 90 degrees angle. That means I can find the magnitude of OP by using the Pythagorean theorem again. So we know the magnitude of OP squared equals to W squared plus the height, which is the z component of the vector OP, which is 2. Then that's replace W squared back, which is negative 5 squared plus negative 7 squared plus 2 squared. So that means I can say magnitude of vector OP equals to square root of the x squared plus y squared plus z squared, which is the Pythagorean theorem in three-dimensional space. Therefore, we say magnitude of the vector OP will be square root of 25 plus 49 plus 4, which is square root of 78. Next, let's find the unit vector of OP. Unit vector OP is actually vector OP divided by the magnitude of OP. So we're going to have each coordinates negative 5 divided by magnitude, which is square root of 78, and the y value negative 7 divided by square root of 78, and 2 divided by square root of 78. Because we have square root in the denominator, that means we have to rationalize it by multiplying square root of 78 both into the numerator and the denominator. Then we're going to have negative 5 root 78 over 78, negative 7 root 78 over 78, and 2 root 78 over 78. Because 2 and 78 can be reduced, so we're going to have our simplified reduced answer. And as you can see, the z-coordinate becomes root 78 over 39. This is called the order pair notation. So if I want to use a unit vector notation, then I will say this much I plus this much j, and the unit vector for z-axis is called k, and this much k. So we're going to have unit vector OP equals to negative 5 root 78 over 78 I minus 7 root 78 78 j plus root 78 over 39 k. Example 2, we're going to draw another position vector OP at 3, 5, negative 4. So first thing we do is we label the x-axis, y-axis, and z-axis. And next, we know our x value is at 3, so we go forward this time. 1, 2, 3. And we're going to go to the right by 5 units because that's a y value of positive 5. So 1, 2, 3, 4, 5. So this point is 3, 5, and 0. And let's do the 5 units on the y-axis too to make a parallelogram for our base of the rectangle. So you do 1, 2, 3, 4, 5, and you make a parallelogram, which is the base of the rectangle. As you can see from this time, the z value is negative 4 now. That means at those 4 points, instead of going up, we're going to go down by 4 units. So 1, 2, 3, 4. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And you make another parallelogram. And now our three-dimensional box is completed. Let's label the remaining points. First, label the origin. And we know this is the x-axis, so it's going to be 3, 0, 0. And since we're going down by 4, so this becomes 3, 0, and negative 4. And at this point, we know this is 0, 5, 0. So when we go down by 4 units, this will become 0, 5, and negative 4. So this is 0, 5, 0. And this point here is 0, 0, 0. So when you go down by 4, will become 0, 0, negative 4. Now, our final point. This point here is 3, 5, and 0. So if we go down by 4 units, it will be 3, 5, negative 4. This is our point P. So our vectors will be go from origin to point P. So this is our three-dimensional vector. So now let's find the magnitude of the vector OP. And we know we can use the Pythagorean theorem for the three-dimensional spaces. So we will have square root of 3 squared plus 5 squared plus negative 4 whole thing squared, which will be square root of 50, which can be reduced down to 5 square root of 2. So we say the magnitude of vector OP is 5 square root of 2. Next part, we have to find the direction cosines. Unlike the two-dimensional vectors, three-dimensional vectors, the direction angles cannot be described as true bearing or quadrant bearing. So we have to use a different notation. We are going to call them alpha, beta, gamma. Alpha is the angle from the positive x-axis to the vector OP. That's called alpha. And beta is the angle from the positive y-axis to the vector OP. That's called beta. And gamma is the angle from the positive z-axis to our vector OP, which is called gamma. In order to find the angle alpha, we need to construct a right triangle again. So I'm connecting the x-intercept to the head of the vector OP. As you can see here, this is a right triangle. And the right angle is right on here. So this is the right angle. In order for me to find angle alpha, I know I have the adjacent side, which is 3, and I know the magnitude of vector OP, which is the hypotenuse. So I have the adjacent side, I have the hypotenuse, I can use cos ratio. So we write cosine alpha, which is adjacent over the hypotenuse, which is 3 over 5 root 2, and rationalize it by multiplying root 2 to numerator and denominator at the same time. You are going to get 3 root 2 over 10. Likewise, in order to find angle beta, I need to construct another right triangle. So I connect the y-intercept to the tip of the vector OP, which is the head of the vector OP. Now, as you can see, this is not a right triangle, and the phi units for the y value, it becomes the adjacent side of the right triangle, and this is the hypotenuse. So I have the adjacent side, I have the hypotenuse. Now I'm going to use cosine again. So we write cosine beta equals to phi divided by phi root 2, which can be reduced down to 1 over root 2, and I'm going to multiply root 2 on both the numerator and denominator to rationalize it, so I get root 2 over 2. Finally, I want to find the angle gamma. In order to find this angle, I need to use this triangle here to help me out. So I draw another right triangle. And as you can see, at this angle, this is a 90 degrees angle. So we're going to label them. Now, because this z value is actually negative, so it's negative 4. So if I do adjacent over hypotenuse again, because the value for the cosine ratio is negative, it will return an obtuse angle for me, which is gamma. So we write cos gamma equals to -4, which is adjacent side, over the hypotenuse, which is 5 root 2, and we're going to rationalize it by multiplying root 2 to both numerator and denominator. Then we're going to have -4 root 2 over 10, and 4 and 10, they can be reduced down by 2, so we get -2 root 2 over 5. Since we are using cosine ratio for all three angles to help us to find the direction of the vector, so we call them direction cosines. And then we're going to take the inverse of the cosine to find all the actual angles, alpha, beta, gamma, which we call them the direction angles. We're going to get 65 degrees for the alpha, 45 degrees for beta, and 124 degrees for gamma. After we have the magnitudes and the direction angles, we can write vector OP in terms of the geometric vectors now. So we can say vector OP equals to the magnitude 5 root 2 and with a square bracket to indicate all the direction vectors, and alpha, beta, gamma are the three direction angles to the three axes respectively, x-axis, y-axis, and z-axis. Example 3, we're going to describe where each of the following sets of points is located, and then we're going to determine the equation of the line or the plane where each of the following sets of points is located on. So for part A, let's look at all the points. This is 0, 0, 6, means 0 for the x, 0 for the y, but 6 for the z axis. So we do 1, 2, 3, 4, 5, 6, the points right here. And there's another one, and 0, 0, -3. So once again, 0 for x, 0 for y, but -3 for the z. So we have -1, -2, -3. It's going to be here. Next one, 0, 0, 2. 0, 0, 2 will be here. So as you can see, all those 3 points are located on the z-axis. So if you look at the similarity between all the points here, in order for them to be lying on the z-axis, both x and y value must be 0. So the equation will become x equals to y equals to 0. And that means it has to be on the z-axis. Part B, the first point is 3, 0, 4. So 3 for the x, 1, 2, 3, y is 0, and 4, 1, 2, 3, 4. So the point's right there. Next one, 2 for the x, 1, 2, 0 for the y, and -6 for the z. So 1, 2, 3, 4, 5, 6 is right there. And the next one, -3 for the x, -1, -2, -3, and 0 for the y, and 2 for the z, 1, 2. As you can see, all those 3 points lie on the green plane. And the green plane is actually called the XZ plane. And if you look at this XZ plane, if you look at all the points on the XZ plane, that means all the y value must be 0, but x and z can be any number. So the equation will be y equals 0. Part C, the first point is 3, 5, 0. So 3 for the x, 1, 2, 3, 5 for the y, 1, 2, 3, 4, 5 is right here. And the next point is 4 for the x, 1, 2, 3, 4, 2 for the y, 1, 2, it's right there. And -2 for the x, -1, -2, and -3 for the y, 1, 2, 3. As you can see, those 3 points, they lie on the orange plane. So the orange plane is called XY plane. And the equation of the XY plane, if you look at all the points here, they all share the z value to be 0, and x and y can be anything because they lie on the XY plane. Therefore, we say the equation is z equals 0. So now, let's look at example 4 now. So if I give you a point, say x can be anything, y can be anything, but z must be 0. That means where are those points located on? It will be on the xy plane. And the next one, it says x has to be 0, y has to be 0, but z can be anything. That means this must be on the z-axis. Example number 5, it says there is a prism, which is a rectangular box, is bisected, means cut in half, by the xy plane. And given the point P is at 5, 8, and 6, and we're going to determine the following. First, I'm going to use the x-intercept and draw a parallel line to the y-axis. And I'm going to use the y-intercept and draw a parallel line to the x-axis to see where the xy plane is. Next, I'm going to label point P, 5, 8, 6. Then, pretending we have a vector from O to P, that means I have to go 5 units on the x, 8 units on the y, and 6 units on the z. That means this part will be 5, and this length will be 8, and the height will be 6. Then, I will be able to find the x-intercept at 5, 0, 0, and the y-intercept at 0, 8, 0, and at this point, it will become 5, 8, 0. Now, part A, we want to determine the coordinate for point F. So we know from this point to go to P is 6 units up. That means from this point to F will be 6 units down. So I know the point will be 5, 8, and negative 6. So therefore, we say point F is 5, 8, and negative 6. Next, we want to find the equation of the plane containing points A, E, G, D. So A, E, G, D. First, let's figure out the coordinates for those 4 points. So we know this is the origin, but from the origin to point A has to be 6 units up. So I'm going to have 0, 0, 6. And from this point to D, it's going to go down by 6 units, will be 0, 0, negative 6. Once again, from this point to go to E, you have to get 6 units up. So we get 5, 0, 6. And from this point to go to point G, it will be 5, 0, negative 6. So if you look at all those 4 points, look at what they have in common. You will see y value needs to be 0 because they are on the xz plane. That means x and z can be anything, but y value must be 0. Therefore, for the plane that contains those 4 points, which is the green plane here, the location is called the xz plane. The equation will be y equals 0. Part C, we want to determine an equation of the plane containing the points D, C, F, G. So D, C, F, G will be the plane that is in blue here. So first thing is, we want to find the coordinate for C. So we know C is directly below the y-intercept by 6 units. So we know the points will be 0, 8, and negative 6. And if you look at all those 4 points here, that means x and y can be anything, but your z value must be negative 6 for all 4 of them. So therefore, we say the equation of the plane is z equals to negative 6. In terms of the location, we will describe it as a plane that is parallel to the xy plane, but 6 units below. Part D, we want to find equation of a plane again containing the points P, B, C, F, which is the pink plane right here. So let's look at the 4 points here. They all share the same y value, which is 8, but x and z can be anything. The reason is this pink plane is actually parallel to the xz plane. That means x and z can be anything, but not y. So we say in terms of the location, we say it is a plane that is parallel to the xz plane, but as you can see, it's actually 8 units to the right. So in terms of the equation, we will say that's y equals to 8. There is another special property of the direction cosines. So we know the direction cosines is always the x component divided by the magnitude, y component divided by the magnitude, and z component divided by the magnitude. So when we square every single direction cosine and add them up together, we are going to end up with this equation here. And when we square them, first of all, the denominator, the square root disappear, and the numerator will become a squared and b squared and c squared. And since they all have the same denominator, you can add the numerator up, and now you're going to have the same value for the numerator and the denominator, so the result is 1. So when we add the squares of all the direction cosines, we are going to have a 1. So now let's look at example number 6. A vector u makes angles of 60 degrees and 105 degrees respectively with x and y axis. This means this is our alpha and 105 degrees is our beta. Now we are looking for the angle between vector u and the z-axis. That means we are looking for gamma. So we know cos square alpha plus cos square beta plus cos square gamma equals to 1. Let's substitute 60 degrees into our alpha and 105 degrees into our beta. Now we get to this equation. And since we're finding gamma, so we're going to isolate cos square gamma. So we're going to isolate it by moving the cos square 60 and cos square 105 to the other side. Then we're going to have cos square gamma equals 1 plus square root of 3 over 4. Then we're going to find cosine gamma by taking the square root. So remember, you have to put in a positive and negative sign. So we get positive and negative ratio of 0.8. And in order to find gamma, we're going to do cos inverse. So you're going to get gamma is either 34 degrees or approximately 146 degrees. Now let's do a summary for the vector in three-dimensional space. Position vector u is written as ABC, whereas the tail is at the origin and ABC is the coordinate of the head. Then we can find the magnitude of the vector u by using the Pythagorean theorem, but within one more component, z. So instead of x squared plus y squared, now we have x squared plus y squared plus z squared. And unit vector will be the vector u divided by the magnitude of vector u. Instead of drawing a two-dimensional Cartesian plane, now we're going to have a three-dimensional one. So the one that is sticking out at 45 degrees, we say that's an x-axis, and y-axis and z-axis will be the one that is going up. And we say the green plane is called xy plane, the blue plane is called xz plane, the orange plane is called the yz plane. And in order to put the point on the three-dimensional space, we move from the origin in the x direction, and then the y direction, and the z direction. Like the vectors in two dimensions, vectors in three dimensions also have algebraic vectors and geometric vectors. Algebraic vectors also have the order pair notation and the unit vector notation. Instead of I and j, now we have I, j, and k. K is the unit vector of the z-axis. In geometric vectors, you still need to indicate the magnitude, but the direction, instead of saying true bearing and quadrant bearing, now we're going to use alpha, beta, gamma, which is the angle with the x and y and z positive axis. So how do we find the angles alpha, beta, gamma? We're going to use our direction cosines to find it. And if you look at your A, B, C, which is the x and y and z coordinate, and the denominator is the magnitude of the vector u. And after you have the direction cosines, all you need to do is take the inverse cosine. Then you can find the angle alpha, beta, gamma. Finally, there's just one special property that you have to know. The sum of the squares of the direction cosine will become 1.